Hi, everyone, and welcome to June 2024 A3D3 seminar. I'm very pleased to be able to introduce our speaker today, who's Professor Gregor Kasieczka from the University of Hamburg. He's been there 2017 as a professor for machine learning and particle physics, and his work focuses on searching for exotic new particles with the CMS experiment and on developing new techniques for simulation and data analysis in fundamental physics. He's also an author on the first textbook on machine learning for physicists, which is deep learning for physics research. So I'm very pleased to be able to introduce Gregor and very much looking forward to his talk today on accelerating discovery in particle physics with anomaly detection. Gregor.
Thank you very much for this nice introduction, and thank you for the invitation. So it's going to be an interesting exercise because I initially did not know what the A3DC acronym stands for, but it turns out I think the talk and some of the goals of this initiative are very closely aligned, and I'm excited about feedback or discussions. I recognize some names at least, and I try to strike a balance between more detailed views on particle physics and a more broader introduction to the topic, to which will come in a second. Just one disclaimer, we seeing as A3DC as a US initiative, which we missed each other very barely. I'm just back from Aspen Physics Center, returned yesterday afternoon, so I'm a bit jet lagged. I hope I'm still somewhat coherent, but exciting discussion will keep me awake. Okay, so let's jump in. As I said, maybe setting the stage for the non-particle physics experts, giving the breadth of this audience. When we talk about a normal experience, we have here a typical German example of a pretzel, which sets the length scale of something between 10 to the 3 to minus 10 to the 3 meters, or for everyday experience. I think the largest pretzel was something like 10 meters, not fully covering it, but it gives you an idea of the everyday life we're talking about. Now, I'm not going to zoom in step by step. I'm going to zoom in one big step to what excites particle physicists by a factor of 10 to the 14. Of course, everything consists of elementary particles, and the goal that we have in particle physics research is to understand nature at this most fundamental level using these most elementary building blocks. And we do this by using some of the largest and most precise scientific experiments ever built. Here, a nice view of the CMS experiment. And of course, the one thing hopefully everybody has heard is the big discovery of the Higgs boson in 2012, which gives other elementary particles their mass and which in a sense completed the standard model in 2012. And now the big question is, well, are we done? And the answer is, luckily, well, if you're a particle physicist, luckily, we would also be happy if we had a complete understanding of nature, but luckily we're not done. And there is quite a bit left to do. And we can divide the things that we still need to be doing into two broad categories. On the one hand, of course, we're interested in measuring the standard model more completely. We've just discovered a new fundamental particle, which means we want to measure its properties, for example, its interaction strength with other particles or its self-coupling. And this is a very big end, and the topic I'm, as the title and the overall theme of this talk implies I'm a bit more involved in, is, and we want to look for physics beyond the standard model, because the standard model is great, but it's not complete. There are holes in the sense that it does not describe phenomena like dark energy or dark matter, and there are also some self-consistency issues. So there is a lot to do, and there's exciting questions, and just to set a bit the environment before we zoom in on the specific work we're doing, I just thought that we briefly review how a particle physics data analysis chain and how the overall ecosystem fits together, because it's quite useful in understanding a few things that are coming up downstream. So the first thing to note, of course, is particle physics is based on the standard model, which is a first principle quantum theoretical model of nature. So in principle, we have a theory that describes everything that happens. The problem is that it's very complex to calculate in all its mathematical glory, and we have detector interactions. But everything that we do is built on this mathematical foundations, and we probe this essentially in collider experiments that the current LHC produced something like 4 million events per second, and we read this out with detectors that have hundreds of millions of readout channels. So this is the first hint. The big data will, of course, play a huge role. And in parallel, I already mentioned that we're based on the first principle simulation. This means we also have massive amount of simulations to do that allow us to interpret this readout of these very complex detectors. And the data, both from the experiments and from the simulation chains, enters a joint reconstruction framework that essentially turns these very complex 100 million readout channel examples into less data that are physically interpretable. So for example, we reconstruct particles, we collect the energies, and we try to do some interpretation of these events. And then we conduct a final analysis that, for example, tries to identify whether a specific type of particle is there. And machine learning is really playing a role in all of these aspects. So I'm not going to go through all of them, but I'm going to focus on a few topics with the common theme that how we can use AI to really accelerate the discovery, especially using something called anomaly detection. Okay, now that we've set the stage, let's go back 40-ish years and think how we discover a particle. So the first example, just as preparation, is here the UA1 experiment from a bit earlier times at CERN, which here we see a Feynman diagram. So for the non-particle physicists, this is essentially a pictorial view how we can imagine the interactions between the particles. So we have a quark and an antiquark coming in. They annihilate, produce a Z boson, which decays into an electron-positron pair. And the main analysis observable that we have is that if we want to discover the Z boson, we can look for a pair of electron-positrons, reconstruct the invariant mass. So essentially, we measure the relativistic four vectors of these objects, combine them to an invariant mass, and then look at the invariant mass distribution. And if we calculate the invariant mass of these two particles, then after adding some selection criteria that essentially reject detector noise or other things that were wrongly identified as an electron, at high energy is really just a very small number of di-electron event candidate remains, forming a beautiful resonance at a very well-defined mass, leading to the discovery of the Z boson. Now, fast forward almost 40 years, or 30 years in this case, to the discovery of the Higgs boson. The story is very similar. The problem is that everything gets a bit more complicated the more rarer the particles that we look for are. So here we have a production Feynman diagram of the Higgs boson. The thing here maybe to focus on is I don't care how it's produced. We have here a Higgs boson that decays, for example, this is just one of several possible channels, into a pair of photons. And we can play the same game. We can reconstruct with very high resolution the invariant mass of pairs of photons, and then look if we see an excess that would correspond to the mass of the Higgs boson. So how does this look? Well, the first thing we observe if we look at the diphoton invariant mass distribution is that compared to the Z boson discovery, we now have many more events. Note that the y-axis scale is something like 10 to the third, and most of these events are background. So essentially other standard model processes that are not the production of the Higgs boson that we look for, or maybe other particles that are misidentified as photons. But what we can do is we still see a tiny signal here on top. And what has been done in the analysis of the Higgs boson is one can, for example, use machine learning to divide all the events that we record into 25 different categories with relatively simple machine learning algorithms, something like boosted decision trees, by using information to the purity and the relative amount of signal one would expect in the different regions of phase space, and to reweight the distribution to nicely enhance this peak. Seeing that we can now more clearly see it. Okay, so this also, of course, led to the discovery of the Higgs boson and the Nobel Prize in 2013. To summarize, resonances are a really great way of looking for new physics. They're not the only way, and we're also going to talk about things beyond resonances, but they're a very nice first paradigm if we look for possible physics beyond the standard model, because they can really offer a clean signature for discovery. Here on the left-hand side is another bit later, after more data collection, example from the again from the UA1 set discovery, and everything was just so much nicer back then, with less backgrounds in the things. Then, in the case that there are large backgrounds present, we can use machine learning to enhance a possible small signal in data. And for the rest of the seminar, we're now going to try to explore how machine learning can accelerate the next round of discoveries. And with this, we'll have 3 different stages. We'll first briefly talk about supervised classifiers, because it also allows us to understand a bit better what type of data we're using. Then the biggest chunk of this seminar will be the topic of anomaly detection. And then we'll have a brief outlook in the direction of foundation models, and we'll see how they slowly appear already in the first 2 parts. So what can we do? I think for this audience, we can skip what machine learning is, but we should talk again about the assumptions that we're making. And the first scenario that I want to look at is almost like the discovery of the C boson, but now we're looking for a hypothetical heavier cousin of the C, the so-called C prime particle, which would be another boson with potentially open couplings, and we're considering the case of the C prime decaying to a pair of top quarks. So now we're assuming we know essentially the final state. We might not know the mass, but we can scan over that. So we assume a new particle that decays to a pair of top quarks. And if we look at an event display of a top quark decay, so this is an event image from Atlas with the proton beams coming in from the left and right. And these 3 cones that are here projecting towards us, these are essentially the energies collected in the calorimeter. So this is the energies of outflying particles, and we want to analyze these energy patterns to figure out if this geometric configuration of energies is compatible with the pattern we would expect from a top quark. And as top quarks are quite a bit more complicated than electrons, we better use machine learning to improve our identification capabilities. Here's another view of this. So what we see here is a jet, which is really, due to the Lorentz boost, collimated collection of particles all coming from the same particle, and initial particle, which would be the top quark. And if we want to analyze this data, the first thing to think about is how to actually represent it in a way that we can interface it with machine learning algorithms. And what has emerged more or less as a somewhat consensus over the last years in particle physics is that one very useful way is to treat these jets as essentially a set of particles. So each of these energy deposits and each of these trajectories we see in the detector, we can see as one element in the set with different attributes that correspond to their energy or their spatial position or any other things that we might measure, something like the energy fraction, different parts of the colorimeter or the displacement of a track. And we can then use different machine learning algorithms to identify that. And since top taking is a quite useful problem, let me just point out in a bit more detail some of the key results here. And these will be shown using an open data set that we generated a couple of years ago, 2019, so basically ancient history, but still useful because there's a lot of results being compared on this data set. You can think of this as something like the MNIST data set of this type of problem. So it's old, it's a bit outdated, but there's so much comparison that it's still useful to look at it. And it consists of 2 million simulated examples of 2 different classes, either top quark jets or light quarking gluon jets, essentially the main background process we would expect in the detector. And as I said, we have very good simulation infrastructure. So we can just simulate these 2 processes, have perfect labels, run it through a very simple detector simulation with a tool called DELFs, and record of something like 200 particles per jet, where we just record the basic kinematics of each of these particles, so their momenta in each of the 3 spatial directions, for example. This is a nice, well-contained supervised learning problem, and we're going to report the results in the 2D plane, where we have on the horizontal axis the number of parameters of the algorithm, which is a very good surrogate for the complexity of the algorithm or the compute cost. Of course, it doesn't translate one-to-one, but it's an easy thing people can calculate, and it's a useful first benchmark. And on the vertical axis, we have a quantity called R30, which is which fraction of top quarks, which fraction of non-top quark examples passes a selection criterion that selects actually 30% of top quarks. So essentially, and we take the inverse of that efficiency. So it's essentially a rejection factor for how much background we kick out with this method. If we now add a bunch of different algorithms on this 2D plane, essentially each of these points is either a different algorithm or a different specific configuration of a given algorithm. We see that's quite a lot is going on, and let me briefly walk through it. So the first thing is that was tried in terms of machine learning that goes beyond simple boosted decision trees or fully connected networks operating on some high-level features, was trying to really use the full information in the chat. And the first thing that was attempted here were convolutional networks, really projecting the point cloud onto a 2D image, which are nice because, of course, convolutional networks know about locality. So things that are geometrically close together belong together. They know about translation invariance, also pre-processing in some cases kill that. But it's not ideal because these projected images are fairly empty. And as I said, sets are a nicer way of representing that. So we can use a purely set-based approach. This is this PFN or EFN particle flow networks or energy flow networks example here that are permutationally invariant, but just having a two-step network that projects everything via summation into a latent space and thereby is independent on the ordering. But we see that alone lacks a bit capacity. We can counteract that, so increasing the performance by more than 50% by using smarter ideas like graphs to first cluster geometrically which particles are close together. So building a structure that introduces some of our physics biases in a very explicit way. Here, bias is for once a good thing, to structure the interactions that matter and then having these particles talk to each other, or even something like an attention mechanism that learns which neighbors are specifically relevant for each other. So if we look at that, let's briefly focus on part T here. This is a particle attention-based mechanism. It has 2 points. This one here, which is a quite good performance, but a very high cost, and it's actually equal or maybe a bit worse than the purely graph-based approach. And we see that the main advantage from this attention-based method really comes when we do something called fine-tuning. So pre-training this method on a larger different data set and then just retraining it on these 2 million examples, which is a way of injecting even more information. So we also see that attention is quite data hungry. The last example on this plane I quickly want to show is even more explicitly building in physics. And the main observation is, of course, that physics events should to some degree be invariant under some transformations of the Lorentz group. So rotations, translations, and boosts. They're limiting factors because we have a defined reference system, which is given by the collision axis, and there's also some energy factors, but there's still some amount of symmetry we would expect. And the nice thing that we can see when we highlight some different approaches that explicitly encode this Lorentz symmetry is they seem to offer, maybe not in each case the best performance, but at least the best trade-off between number of parameters and the complexity of the model. So we do have some type of Pareto frontier potentially. Also, of course, everything is with a bit of noise. But overall, Lorentz symmetry is a powerful physical constraint that we can enter into that problem. Now, I'm not going to talk about all the results that are being obtained with tagging techniques, but they do work on data. They're being explored by the different experiments. And here's just an example that for CMS, over 40 publications cite the latest tagging paper, essentially assuming a specific type of signature and using taggers to enhance it. Now, here is the most depressing plot of this presentation. and maybe of the field in general, this is an overview of searches for different scenarios of exotic new particles conducted by the CMS experiment. Each of these lines corresponds to one final state, meaning corresponds to one specific analysis assumption or several, I think, no, only one analysis for each of the lines. And the horizontal mass shows the excluded mass scale of the new particles. This is essentially a map of all the places that we looked for new physics and we did not find it there, which is still very useful because it puts limits on the allowed theory space. But if you're an experimentalist hunting for new physics, that's of course also a bit depressing. You can use indirect methods like precision measurements of the standard model to learn more, or, and that is what I'm going to focus on, we can try to further loosen the constraints on the way we discover anomalies. And before we talk in details about the algorithm, let me first just give you a pictorial example to kind of get the idea across. So let's assume we want to find anomalies on the Golden Gate Bridge. Here's just a picture taken from Wikipedia, and you see here a generation frame. So we're going to invoke DALL-E in a moment. The first thing we do is we erase some part of the image. You can think of this already in physics language as defining a signal region cut out. And now I've strategically placed it here, but we could put that really anywhere in the image. So we've defined our signal region cutout. And then we ask DALL-E 2 to interpolate the background. So we're using a generative model to use information maybe seen from other images and the context of the rest of the image to fill in the hole. And if we now look at this, it doesn't look perfect, but it's still a pretty good filling in of the background. So maybe the structure is a bit skewed. You see it doesn't get the fact quite right that these lines should be very straight. But still, if you look at it very casually, you say, oh, that's still an image of the Golden Gate Bridge. This already tells us something that we'll encounter a bit later, namely that essentially there will exist some trade-off between the quality of the generative model and the quality of a classifier that we're going to use for anomaly detection. And they can't be too mismatched. I already said classifier, so what are we doing with this downstream? We take original images, we take these interpolated images, and we train a machine learning-based classifier to tell these examples apart. Here, in this case, of course, I just have one image. You can think that in a practical application, we have many, many, many examples, and we actually have enough to train and evaluate the classifier. Okay, so in this case, if we have no anomaly, of course, the classifier does not see a difference. If we now inject an anomaly and have Godzilla attacking the Golden Gate Bridge, we can play the same game. I already put the plush Godzilla in the place where we're going to do the cutout. So we just do this very quickly. And what we get, of course, is if we compare now the original image and the interpolated image, we by eye and also with any classifier see there's an anomaly in this specific spot. Of course, this only worked because I put the generation window in the spot where we had the signal, but this just means we will need to scan the signal window over different places as we're going to do in a minute. Good. So we have a strategy how to discover anomalies. What does this allow us to do in terms of physics assumptions? So what it allows us is, let's revisit the assumptions. This is what we had before. So we needed to assume what particles the C decays into. Now, we don't anymore need to assume the mass and the type of this resonance that's produced here. And we also don't really need to make any assumptions about what types of particles are produced here. So this is the generalization that we can achieve. There is still some strong assumptions. Primary assumption is that the particle that's produced here still decays into two jets that then decay further. We don't really say what they decay in, but we assume that this is a resonant particle decaying into a pair of jets. I'll talk towards the end about further efforts to generalize this picture, but this is what we have most results for, so let's dive into that. The specific approach that I'm going to talk about is something called cathode, classifying anomalies through outer density estimation. And we really want to build something that identifies a resonant anomaly in a way where all the machine learning tools that are going to be deployed are fully trained on data. So we're using simulation to understand the structure of this problem, but the final training is all done on data. This is done in such a way that we need to pick one feature, in this case, the Dietrich invariant mass, where we expect, as we've seen in the example of the C, the Higgs, and the C prime before, the resonance to appear as a well-defined peak, while the background, QCD background, is a smoothly falling distribution. So we have one resonant feature that is the invariant mass, and as opposed to this nice drawing here, we also assume that the signal is to be too small to just be visible in this inclusive distribution. Otherwise, it would be quite easy and we would have already discovered that. In addition to that, we assume a number, in this case, 4 additional features in which we don't make any specific assumption about how the new physics behave. We just hope, on the quotation mark, I'll talk about what that means also a bit later, that the signal will differ from the background in some way, at least in some of these features. So the more features we use, the more chance we have that the signal differs in some of them. We'll come to that. In this specific case, we took the masses of the 2 jets and some substructure variable. This tests how 2 prong-like, so how much like one particle decaying into 2 more particles, these 2 jets look. And 4 features, of course, is a very small number. Now, we have the setup. And what we now want to do is to replicate the example I gave with the Golden Gate Bridge. So the first step was to train a generative model. We don't train a generative model to generate the mass distribution. This is just a simple one-dimensional thing. No, we train a generative model in these sideband regions. So essentially selecting, splitting up the mass distribution in different regions, cutting out the part where we're looking for a signal and only looking in the sideband regions at the 4 other features. And this is an obvious question. Here in this picture, I picked the signal region to be exactly in the right spot. In practice, we need to scan over it. Okay, so we train a generative model, and generative model means that once we have a set of examples, we train a mapping so that drawing from a random distribution according to this function reproduces the shape of the data. And of course, the function in case that we're using will be a neural network. And there is quite a bit of work going on in building different type of generative models. You likely heard about generative adversarial networks, variational autoencoders, flow-based models, diffusion models, flow matching, and so on. And the random distribution, or the latent space, as we'll be using that in a few moments, is typically a Gaussian distribution. There could be a whole separate talk about using generative models in particle physics specifically for simulating different aspects. We're not going to do that. I'm just leaving this here as a teaser for the different types of environments where generative models are used for simulation. Here in this specific case, we're using a normalizing flow. So essentially something that is differentiable, perfectly invertible, and has a well-defined and easy to calculate Jacobian matrix, which allows us to directly use a maximum likelihood objective to train the network. So we have a structured mapping between the data space and the latent space that can be run in both ways, which means also that the latent space dimensionality needs to be the data space dimensionality, and that can be trained to a very high generative accuracy. For this specific example, we're not going to use any information about being able to calculate the likelihood, but there are alternative anomaly detection techniques that use that. So, after this brief aside on generative models, so what we're doing is we train a generative model in these other features conditioned on M and interpolate and sample it into the signal region. And you see it already here in these small diagrams, but let me pull that out. So this gives us 2 distributions. The first one is the sampled output of the generative model, which if we picked the width and the position of our signal region correctly, gives us a distribution, and if the generative model learned correctly, gives us a distribution of the background learned in situ. So this is really the background taken from data and transported to another region in data. And if there's no interesting new physics showing up in any part of the distribution, then of course the actual data in the signal region should also just behave and be correlated according to the background distribution. So these are the red dots here in the signal region example on the right-hand side. But if there's an additional new physics signal on top, so some C prime or other particle with different correlations than all the background examples, these would look different in these distributions here. And a simple classifier trained on these 4 features would be able to distinguish these 2 sets of examples. So at no point we need to inject actual signal Monte Carlo into this classifier. We will need it though to understand the results of this. Okay, so we train this classifier, and then we can look at the output of the classifier, which gives us a probability between 0 and 1, and just cut on different thresholds of the classifier. And the more data-like events are, this is essentially the part of the tail of the distribution that is selected as the events that differ most strongly from the background, which are the interesting signal candidates. And we can first look how much such a selection on the classifier would enhance a potentially injected signal. We show here the significance improvement, which is really just a very rough estimate of the potential sensitivity by saying this should scale roughly Poissonian. So we take the fraction of the signal examples that pass the selection criterion and divide it through the square root of the fraction of background examples that pass this criterion, giving us essentially an enhancement factor by applying this method. What I described here as cathode, this is this purple line, and we can see that it's almost as good as an idealized version. That would essentially assume that we have a perfect density estimator for the background. It is a bit worse than a supervised classifier where we inject signal Monte Carlo, so where we assume that we know what we're looking for, but the significance improvement factor of something like 12 or 13 at the peak really means that if we had an initial significance with an initial signal with a significance of 1 standard deviation, applying this would give us 12 standard deviations, which is of course a bit optimistic because some detector and realistic effects need to enter, but this is essentially the way how to read this example. I already said this is not realistic, but this is very motivating. And if we want to get more realistic, there is a recent result out by CMS that does exactly this style of anomaly detection on the full run-2 dataset. This so-called CMS anomaly search effort or case analysis used 6 different anomaly detectors in parallel. I'm focusing here, as I said, on the results that we achieved with cathode, but there are other anomaly detectors in there as well, including some, especially from the MIT group, with A3D3 contributions. So the first thing we can do is we can play the same game and test the expected gain in sensitivity by injecting different signals, and this mainly serves us to see what are the type of anomaly detectors. So I mentioned this cathode, 2 different versions of it, one with the features I just described, one using additional flavor information. And we see that for a signature of 1 jet decaying to a pair of new particles, each decaying to a pair of quarks, so some relatively simple substructure, these methods outperform a benchmark, which would be either an inclusive search, so not cutting at all at the jet features, or just using classical substructure techniques. How does the method proceed? So I before talked only about the significance improvement, but we still need to turn this into a full statistical analysis. And the way this was done in case was to first train this method on data, use cathode to select the 1% most anomalous events, and then just perform a traditional bump hunt in the spectrum. So this assumes that the cathode method does not shape the background distribution too far, which we can test by running the full method without the presence of signal. And if we convince ourselves that this works, then we can just perform a bump hunt and look at the significance of these things. As you already see in this plot, unfortunately, there is no strong signal-like outliers. So in all regions, the data and the background-only distribution agree fairly well. I think the maximum significance across all the methods and across all the possible signal regions was something like 2.9 sigma. local sensitivity only. Okay, so we do not see a signal strong signal like outlier. So the next step is to set limits, and this is an interesting complication in the business of anomaly detection, because so far, as I said, everything was done on data only. But if we want to know for a specific signal, if we would have been able to discover it and with which strength it would have needed to be there in the data for us to have been able to discover it, we need simulations. And you already noticed by the complicated way I'm saying this, that this becomes a bit subtle. So what was carried out is to really inject different types of signals with different strengths into the data, rerun the weakly supervised anomaly detection like cathode, and try to see if it would have been discovered, essentially looking for the crossover point where we would have extracted that. And well, these are quite many results, and I think the numerical values are less interesting than the overall trend. So here, just as an overview, altogether, this procedure allowed to set limits for 43 different signal scenarios, with an amount, if I remember correctly, for cathode of training something on the order of several thousand classifiers for all different variations of signal strengths. In total, typically, we observe a small integer number of improvement in terms of sensitivity over the inclusive search with a bit of scatter from the different methods. There's quite a bit of details we can read into. One of the effects is, for example, whether B quarks are included in the signal or not, which makes it a bit easier for cathode B and a bit harder for the standard cathode method. There is also, for example, effects like if we have things that are not easily captured by the two primary features, the methods that use the full event information, like a variational autoencoder, do a bit easier. But altogether, this allows setting a bunch of limits and improves the scope of anomaly detection we can do. You can also stay tuned for a specific CMS paper on the details of all the methods. So what is out for now is just the physics result, and a bit more detailed ML interpretation still coming. Now, we said we assumed pairs of jets, but so far we only used a very small number of features per jet. Can we do more? And the answer is yes, but it's a bit difficult because, as I said, we don't know a priori which feature is anomalous. So naively, just adding more features would be something like just adding lots and lots of noise. This is symbolized here again by a significance improvement curve, adding more and more Gaussian type features, features that are just pure Gaussian noise. And we can see for a simple neural network, the performance degrades quite strongly. One nice observation is that, interestingly, boosted decision trees, so specifically his gradient boosting, are for these high-level features much more robust against noisy inputs. And we can see here that with BDTs instead of neural networks, we can stay quite stable until something between 10 or 30 features. This just allows us throwing more and more inputs at the problem. This is again for the physics, now with physically motivated inputs, and just steadily improving the performance to a higher and higher significance improvement factor. We can go even one step crazier. Instead of using physics-motivated features that are still calculated, we could use a pre-trained machine learning model that was just trained as a massive classifier between 188 different classes of jet substructure, use the latent space of this model as input features, and then just train a downstream classifier that uses the 128 latent variables as its input features. Sorry, I forgot to put the tag here. Javier et al. Were also involved in this, so there's also some A3D3 linkage. And the main improvement, of course, is that this allows us to push the discovery potential towards even lower significances. We can go even potentially one step crazier and use progress in generative models for low-level distributions for all the particles to really go from a bunch of high-level features to all the constituents given an even higher potential maximal significance improvements. Also, currently the German is at a slightly higher number of injected signals. Okay, I'm going a bit fast because I want to end in the next few minutes to not go too much over time. So let's make these things a bit more crazy still. What if one jet goes to missing energy? Then we lose the capability to reconstruct the invariant mass, but maybe we can still salvage this. And we could salvage this if we had a classifier that was independent of the missing transverse energy. Missing transverse energy is the variable that captures essentially everything we can know about the energy that went missing. So if we had a classifier that was independent of missing energy, we could use something called the ABCD method, which particle physicists know quite well, which essentially assumes that if two features are independent, any ratios of the counts of examples in these different regions will come out as even. So for example, the number of D events compared to C should be the same as B to A, and we can just arithmetically manipulate this to get the prediction of examples in this A region, which would be at high missing energy, which is where we expect the signal to show up, and at high classifier value. So if we can train a classifier value that pushes signal towards the edge and that is independent of missing energy, we could have a chance to do an analysis based on ABCD. One way to achieve this is again to use normalizing flows, not now via the capacity of being able to sampling. But remember, a normalizing flow is something that learns to transfer from the data space into a latent space, where we just assume a base distribution such as a Gaussian distribution. So if we train a conditional normalizing flow that is trained on missing energy on the background-only sample, we can learn a mapping from how the background looks to a distribution that is per definition, because we do it conditionally as a function of missing energy, so the remaining distribution will be independent of that feature. The only downside here, to be explicit about this, is that we need a control sample that is background only, which would either need to come from classical simulation or which could be obtained via a controlled region in data. So the example we did is looking for a set plus jets with the set decaying invisibly, and we use gamma plus jets as photon plus jets as a benchmark, as a reference sample. So once we have the background in the data projected into this latent space, we can use a classifier to learn this mapping distribution, and then, as I said, construct an ABCD plane and analyze that. The nice thing, if we do that, is that the background prediction to something like cutting to a factor of 10 to the minus 3-ish remains stable. After that, the model became a bit unstable, but since in cathode we use 10 to the minus 2, the range 10 to the minus 2 to 10 to the minus 3 is actually what we need. And if we look again at the significance improvements curve, we can see not quite as large numbers because we lose information in missing energy, but enabling this channel at all is quite cool. And we can see, for example, that with the cut value of 10 to the minus 3, we're able to improve an initial signal on the order of 2 sigma to something on the order of 5 sigma. So still aiding a potential discovery. Now, to close, we can look at what happens if events even get weirder. And this is just a teaser that one very orthogonal to what I explained strategy for discovering anomalies are autoencoders. So having a neural network that maps from data to latent space, from latent space back to data in such a way to learn a compression for the examples it has seen, and then applying it to unseen data, flagging things that behave differently, that can't be compressed and decompressed so well. And we can actually run this in the online event selection system of the experiments. And this is running now in a testing crate at the CMS level 1 trigger. This is really so many A3DC contributions that I think you best ask your local colleagues about this, but this is something very exciting, going on to producing real anomalous enhanced events in data. So to almost close, we've come a long way since the 80s, and anomaly detection can really enhance the way we try to discover new physics. And as a last word, I just want to add that with foundation models that are being now explored for large language models, in the sense of machine learning architectures that are trained on massive data sets, and then fine-tune for a specific problem, we might even get more leverage. So we already observed, for example, that the best performing top tagger is a fine-tuning from pre-training to the specific problem. You could imagine going further and saying we have one backbone model for all type of data analysis at the LHC that just has a very slim and retrainable head for a specific problem. Just to show one specific example of this, so we can use a GPT-like architecture that's running on tokenized version of chats, pre-train it only on unsupervised generation. So in principle, this could use more or less the raw, unfiltered output of the experiments without any classification as a training baseline to have a very large amount of statistics for unsupervised pre-training and then fine-tune for supervised classification. And in this example, we see something like a factor of 10 to 100 improvement of data efficiency for the specific problem. And this is really one other aspect, how we can greatly accelerate the discovery chain, because if we now think of either anomaly detection or model-specific searches, if we need a much less amount of specific data examples or specific simulation examples to train a very high-performing classifier, of course, this gives us much quicker sensitivity with much less examples in compute. So that's it. Thank you very much for your attention. I hope this was exciting. At least I'm very positive about the future we have with anomaly detection as applied to particle physics. Thank you very much.
Okay, thank you very much, Gregor. Let's see if we have any questions from our participants. Jonathan?
Hi, thanks so much. It's a really great talk. I'm here by kind invitation of Mark, because I'm at UIUC, but I'm not actually a member of A3D3. The Pareto frontier that you mentioned for the top quark tagging data set, do you know of anybody that is trying to calculate that, or is that basically just empirical right now?
Purely empirical.
Okay.
Yes. Do you have thoughts on how one could calculate it? I just keep throwing that out there, hoping that at some point somebody bites. So
I've been thinking about this, and one of my students who's been thinking about this too is also on the call. I don't know exactly what to calculate, but like it would be great to indeed show that there is like some calculable thing, because one question is like, should that really be a straight line on a log linear plot, or should it be a power law or something? But
yeah,
okay.
So I'm okay. So maybe two comments. The first one is, I mean, this is an inverse axis, so I'm not sure if calling that linear is the right way. At least it's some transformation of linear. Okay. The second data point, I have not talked about this point here in the middle. This is bit of an annoying acronym, is a distance decorrelated forward feature selection on a specific feature sets. I find it interesting because Pelican here and Pelican here is really the same method. It explicitly encodes Lorentz symmetry, just with different degrees of capacity for the network. This thing here is an entirely different approach, but still uses as a baseline physically calculated features that we know have good properties. So that's why I kind of find it fascinating that lies there in the middle. But if you want to start calculating, maybe just looking at the different ends of the Pelican spectrum is a good starting point. The other thing here is, of course, that the party up here is a bit of an outlier, and that's not explicitly physics inspired. That's just pre-trained on a massive amount of data. So we don't know whether physics ends here or whether there could also be something up here. So
great, thanks.
Okay.
More questions for Gregor from anyone? So I'll ask a relatively naive question, at least for particle physics, because I'm an astronomer by background. But I mean, one of the problems with these large language models, the foundation models, is the tendency of them to hallucinate in certain circumstances. And do you think that there's a potential of false positive discoveries in particle physics with one of these models hallucinating? And detecting something that's just not there, it's an internal inconsistency or whatever.
Let me say something controversial. Hallucinations are great. Not in the usual application of large language models. There, of course, it's not problematic, but the way I need to jump maybe a bit forward. So if I talk about foundation models, I think there's really two very orthogonal ways you can think about that. The one would be something very top-down, where you still stay in the realm of language models and try to combine language knowledge with physics insight. People are working on that. That's Polymath AI, for example. Or you go bottom-up. Bottom-up would be learning different physics tasks and showing transfer learning between them. And this is what we've done here. And the physics task is very explicitly generation. And I don't have the plot in here, but essentially when we do generation in the physics context, we don't care about individual examples. So, we don't look like, is this something hallucinated with a dog wearing a stupid hat or something like that? But we always look at distributions, so distributions of individual features, or something like a classifier metric that really compares the ensemble of generated examples to the ensemble of some held out training data. And this way we can relatively rigorously check if the generative model is producing new events that are in distribution, or whether it's just producing out of distribution stuff. So we can catch that more easily because, of course, we have the statistical tools to meaningfully talk about the distributions of these examples, because they're much simpler than what's going on in actual, let's say, photographic images.
Sure.
So I think we can calibrate the generative models well enough that we can be sure that we trust their output and avoid this type of hallucination.
But you're still fundamentally constraining yourself then to a known distribution based on known expectation.
Yes, I think that is fair to say. So
the unknown unknowns would still fail on that sort of model then.
It becomes a bit difficult if we talk about foundation models, because we can use them in different ways for specific tasks. So I think specifically for generation, we need to make sure that if you say, I want to use it for a generative task, I want it to match the distribution that I trained it on, because otherwise it's doing a bad job at generation. Yeah. If you're talking about anomaly detection, one way would, for example, to just replace both parts of the cathode chain that I explained with the foundation model. So the generative part will still learn to mimic a certain distribution, and then the classifier would be able to pick out any differences between the actual data and this learned distribution. And the idea would be that both parts are more performant in the sense that they do better, but they still have independent quality metrics that we can use to constrain them. Unknown unknowns are much harder with such a model. I don't think I've seen an example where somebody realized something like an autoencoder in that context, but that would be interesting to think about whether this makes sense.
Yeah. Thanks. Yeah, that's good. Okay. Any more questions for Gregor from anyone? If not, okay. Thank you very much, Gregor, for this very interesting chat. I'm hoping that some more A3D3 people will catch up with it online and maybe contact you with the questions offline.
Sure. Thank you very much. And of course, always happy to hear any type of feedback or questions. Thanks a lot.
Great. Okay. Thanks, everyone. And we'll see you next month for next month.